So, now this PIR we can also use this to get the peptide match. In the patterns and peptide, what is the difference?
Peptide will be specific.
Peptide means exact match.
Exact.
Right. For example, some peptides tend to aggregate. Right. So, even if you make a small change, one residue change, the character will change. In this case, you require the exact match. For example, if you have AITCV, this is yes, but if you get AICCV, this is not. So, if this is the case, we need to find exact match. So, here you can do the peptide match. So, you give the peptides and exactly you can match. In the pattern search, you can write in this way AI star CV. This you can include this and this, but in the case of peptide match, this is okay, but this is not okay. So, for example, if you give any specific peptides and you search right in this any database, and if you see these are the proteins which we have exactly the same peptides. For example, if you are interested to find the peptides which aggregate, right. So, you can give the peptides and check all the sequences and see which sequences contain that particular region, and are there any similarities, right, or differences, you can do the analysis, right. You can do a lot of projects on this aspect. Then once this is done, then we can also construct some type of matrices, right, because we discussed about some motifs and discussed about some patterns and discussed about exact match. If you look into different sequences, and then we can try to develop some sort of matrices. Earlier we discussed about multiple sequence alignment and conservation score. What is multiple sequence alignment? Aligning 3 or more sequences, right. If you have 3 or more sequences, you align together, right, and finally you find an alignment. How to use the alignment for conservation?
Find the residue.
As you can see the residues which occur the same position in different sequences, right. Based on that we can calculate the conservation score and see which residues are conserved. So, here the PSSM, this is the position specific scoring matrices. This also provides your patterns which are inherent in the multiple sequence alignment in homologous sequences. How to do this I will explain now. If you have multiple sequence alignment, you can see whether you can find any inherent patterns. So, how to do this? The basic idea is to match the query sequences, right, against the database sequences and the alignment table, and give that high weightage to the conserved position, with high weightage for the positions which are highly conserved than their variable. Then you can see some type of matrices. This will tell you, okay, for example, position number 15 alanine is present, what is the probability of having alanine at position number 15? This is fine or not? If it is good, then you can exactly match, right. Then for the many prediction algorithms they use, okay, they construct a matrix, then if you can any sequence and see what is the probability of particular residue at particular position. If this is the case, that can be part of helix, right. We can use this matrix for many prediction algorithms. How to obtain these profiles? So, these profiles we can obtain with a set of probability scores, that for each amino acid we for in a protein we have a probability score to be for the particular position in the during the alignment. So, in this case, what are the various applications compared with other measures, for example, conservation and all. So, it get greater accuracy when you align the different distant related sequences, and the conservation patterns also facilitate the identification of the homologous sequences, because we have the high score in the case of the homologous sequences, and you can see the patterns which are useful to classifying the subfamilies within a set of homologous sequences. Then if you look into the various secondary structure prediction algorithms, or prediction the accessibility, or predicting the binding sites, different prediction algorithms, they are reliable if they have the multiple sequence alignment rather than a single sequence. Getting a single sequence, they can construct profiles, right, like hydrophobicity profiles, right, or you can get the propensities. Rather than the single sequence, if you use the multiple sequence alignment, right, I will discuss in the next classes when we discuss about the secondary structure prediction, you can get that the prediction results are more reliable than using just a single sequence. So, now how to construct PSSM matrix, right. I will give you the examples how to construct the matrices. So, what is the basis for the PSSM? Sequence alignment. So, it will give you the frequencies of each residue at each position in a multiple sequence alignment. For example, if you see one sequence here, GHE, GV, GK, VV, KL, GA, GA. So, I have few sequences, I put for example 5 sequences, they are used in the multiple sequence alignment. From this, based on the first sequence, the one which are the same residues or conserved residues, they are highlighted. So, if we take this is position number 1, 2, 3, right, take the position number 1, what is the probability of having G in position number 1, what is the frequency of occurrence of glycine in position number 1, you can see 1 because there are 5 cases, 5 sequences, and among the 5, so 5 by 5 all are glycine, so 5 by 5 that is equal to 1. Likewise, what is the occurrence frequency of glycine in position number 4?
2 by 5.
That is 2 by 5, right, this is 2 divided by 5, right, this is equal to 0.4, right. So, now we have the 20 different amino acid residues here and the sequence here. For the first case it is glycine, right, it is 5, here 5, and the second one you can have the 5 in the case of H, and the third one we have 5 for E, and the fourth one distributed G 2 times, F 1 time, and K 1 time, L 1 time, right, distributed. So, now if you have the number of sequences and make the matrix, several cases the numbers are 0, if you see there are many zeros. In the case of zeros, they add few numbers, right, add a number, this is called a pseudo count, right, to avoid these zeros, right, because when you take the logarithmic. So, what they do, for example, if you take the amino acid sequence, what is the probability of each residue to be in a particular position? 0.05, right, 1 by 20. So, what they do, so they add 1 at the top and then 20 at the bottom, and then they find the pseudo count. For example, in this case they put 5 plus 1 divided by 5 plus 20, right, what is the value, then 6 by 25, right. So, we get the number 0.24, and then this is the one f dash ij, then they normalize with this qi, q is the expected frequency of a residue I at a particular position, right, in a random sequence. They got several sequences, right, then what is the expected frequency of a particular residue I at a particular position, because all the residues are not randomly distributed in amino acid sequences. If all residues are randomly distributed, all the sequence whatever the sequence you take, each residue should have 0.05, but it is not the case, right. I showed the data from the Uniprot, some residues are biased, for example leucine valine they are highly dominant, and tryptophan and cysteine are less frequent in amino acid sequences, right. So, now if you take any sequence, what is the random sequences, what is the frequency, they divide the qi, then take the logarithmic, that will be a score. Like the PSSM, there is another matrix that is called weight matrix. This is also frequently used in the prediction algorithms. How to get the weight matrix? For example, if I gave 4 different sequences, this is a DNA sequence. So, first we construct the matrix for the occurrence of each nucleotide at different positions. So, how many positions? 6 positions, right, 1 2 3 4 5 6. How many sequences? 4 sequences, right. So, you can put first A, right, all the 4 sequences have A, second one 3 Gs and 1 A, and the third one 1 T and 3 Gs, right. We can fill this matrix based on the sequence alignment. Then you convert this into score, into weight matrix. If you look into this alignment, you can see consensus here is A, right, this is G, because there is 3 times, here will G 3 times, here G 2 times, here all everything has equal probability, so they put N, this is how they put this consensus here. So, here also they make a pseudo count, so they add the probability, right. For example, if you have one more sequence, now there is 4 sequence, if you add one more sequence here, what is the probability of having A at this particular position? 1.
First position. 1.
Yeah, for example, if you add any sequence here, this is sequence 4, now I put sequence 5, I can write anything here, right. What is the probability of having A in this position? 1 by 4, because it can be A, it could be T or C or G. So, probability of having A is 0.25. In the case of protein sequences, if you have several sequences and if you add 1, then the probability is 1 by 20, right. So, here this is a pi. So, this is equal to 0.25 in the case of DNA, that is 1 by 4, and this is equal to 1 by 20 for the case of amino acids. So, now they use Nij, right. Here Nij equal to 4 plus the probability. If you add one more, what is the probability of having that nucleotide? This is 0.25 divided by, now the number of sequence will be added to 1, 4 plus 1. So, here 4. So, now add one more sequence. So, 4 plus 1 equal to 5. So, in this case you can get the values, this equal to 4 logarithmic of ln of 4 plus 0.25 divided by 5, right, normalized with this pi, that is equal to 0.25. You do the calculations, this equal to 0.85 divided by 0.25, this equal to logarithmic of 3.34, this equal to 1.2. So, this is the number. For example, if you take this 0, what could be the value? The weight matrix, this is 0, 0 plus 0.25, right, divided by 5, then the whole thing normalized with 0.25. So, finally, you get the value of minus 1.6, right. So, you can convert this any alignment matrix, we have a lot of sequences or the alignment data. So, you can convert this matrix into weight matrix. Now, from this weight matrix, now if you have any sequence, or you can have to identify the secondary structure or any specific binding site of any niche sequence, you can compare. Okay, if this is belongs to a binding site, then if you have the same A in this particular position, then you can see that this A could be probably a binding site residue with any of the particular protein, right. So, likewise they use this weight matrix for identifying any binding sites or any public applications. Okay, there is one more case. So, you can see we use the cyblast. What is cyblast? Position specific iteration blast, right. So, in this case we align several homologous sequences, right, and then we use different iterations. For example, if this is a protein and this is the possible 20 different amino acids, they give some big numbers. So, big number, so first we need to normalize these numbers. So, then we know which one is the preferred one, which one is not preferred one, because it has both positives and negative scores depending upon the preference of these residues at any particular position. So, in this case you can normalize between 0 and 1. So, how to normalize the values between 0 and 1? So, you can use this equation, x minus minimum divided by maximum minus minimum. For example, this is I give 5 numbers, okay, this is the lowest one. So, what is the expected value for the lowest one? 0, right. If we use this equation, right, 1 minus 1 divided by 9 minus 1, this equal to 0 by 8, that is equal to 0. So, that is fine, right. So, if you have the highest one, right, what is the expected value? That is equal to 1. So, if you use this one, 9 minus 1 divided by 9 minus 1, this is equal to 8 by 8, right, that is equal to 1. So, now if you take any other values 5 or 6 or 2, what is the expected value? Between 0 and 1. So, we take this 5, so we get these numbers 5 minus 1 divided by 9 minus 1, this is equal to 4 by 8, this is equal to 0.5, that is fine. So, we can use this equation to normalize. So, now if you see these numbers, right, very high numbers, they are normalized between 0 and 1, we can see some numbers such very high and some numbers are very less. For example, if you see any high numbers, okay, this is high 0.64, so here this is 0.59, right, some numbers are very highly preferred and some residues, right, this is the less preferred ones. So, now if you got different numbers, it is also possible to combine these numbers and make a 20 by 20 matrix, right. Instead of using different numbers, it is also possible to take 20 by 20 matrix. In this case, you can uniformly use this for different cases. How to do this? For example, if it is EC, they take all the E's here, here is E, here is E, here is E, and C is here, here, here. So, take all the values taken together, finally you will get the average value of E and C. Likewise, if you see LA, combine all the LAs and you get the numbers. If you take QD, what is the value for QD? This is Q here, this is another Q here, right. So, D is here, right, this one, this is one, this one. So, add up these numbers and we will get the average value, we will get the matrix. So, finally, you will get the 20 by 20 matrix. This also you can use for several applications or several prediction algorithms. So, we discussed about the position specific scoring matrices and weight matrices, right. So, there are several potential applications. For example, the major applications if you see, predict the secondary structures, right. You need a sequence, if you give the amino acid sequence and there are several secondary structure elements, for example alpha helices, beta strands and the coils and all, and we will discuss in the next class, right. So, how to predict which regions constitute alpha helix and which region is responsible for this formation of beta sheets, right. We can use the PSSM, right, you can get the predicted secondary structures. Then you can also discriminate proteins from different classes and different functions and based on different structures, that you can also use this PSSM to get the information. Then also you can also identify the binding sites or functionally important sites. So, here also you can see, right, which residues are functionally important in any given protein. Likewise, we have several applications in bioinformatics areas, right, and you can relate this data with the experimental data and you will see this PSSM as potential applications in various prediction methods. Till now we discussed on various aspects. So, we will summarize what are the various aspects we discussed today. Hydrophobicity profile. So, what is hydrophobicity profile? It is a sequence versus hydrophobicity. It is a plot connecting amino acid sequence versus hydrophobicity values. So, what are the applications of constructing hydrophobicity profiles? You can get some patterns, right, and these patterns resemble any specific regions in a proteins based on structure or based on function. Typically, for example, helices, strands, transmembrane regions, right, when you binding sites, right, you can see different patterns of hydrophobicity and you can use these patterns, right, to identify these regions. Then we discussed about specific patterns, right. So, in PIR we can search for patterns, right. How to write a pattern? We can by square bracket that represents what? Any residue, any allowed residues, right, and then any conserved residues, right. How to define conserved residue? Write the name, right, the name of the same amino acid. Then any residues by x, number of times put n, so any number, and curly bracket represents excluded, right, if those residues are not allowed in that particular position. So, you can write the patterns, right. So, what is the importance of identifying patterns or the peptides? You can identify motifs, or you can see any inherent residues, right, for any specific features, right. You can check in the uniprot sequences, right, and see whether there is very specific for any type of proteins based on structure or function, right. Then what did we discuss after that? PSSM or position weight matrix. What is the principle based on PSSM or weight matrix?
Positional conservation.
Positional conservation, right, it will give you the positional conservation, right, for that multiple sequence alignment. They take the alignment, right, and they get the frequency and they convert the frequency into score, right, you can the matrix. So, you can use this matrix and the matrix has several potential applications. So, in the next class, so we will discuss mainly about the using several features, and making these features requires a data set and how to construct a data set, what is redundancy, what is non-redundancy, right, how to define this type of redundancy, right, and what are various methods which are available in the literature to obtain these non-redundant sequences and so on. And later on we will see the potential applications and you can merge these features and the data set and find your problem, and then you can use, right, to see what are the potential applications of using different bioinformatics tools. Thank you very much.